Alright gang, here we go. Chem 2 Unit 11, talking about how we can relate what we just learned about free energy and spontaneity, and how we can relate that to other things that we've been doing over the last couple of weeks. And specifically, we're going to relate free energy to equilibrium. I know, it's almost too exciting to be believed, but it is true. It is true. Okay, so so we get this equation here, and it doesn't really matter how it was derived. Don't worry about it so much. But the idea is that, remember, when we have this little symbol right here, this implies that we are talking about that thermodynamic value at standard conditions. And it's always helpful to be able to know, how do I find out what that value is under non-standard conditions? Because very often we find ourselves at non-standard conditions. So we get this formula here, where our Gibbs free energy at non-standard conditions is equal to our Gibbs free energy at standard conditions plus RT natural log of Q. Now R is is the same R we used when we talked about energy. Okay, so that's our 8.314. And then the big thing to remember, this got other units involved, but the unit you gotta watch out for is this guy's in joules. And a lot of times our delta G is in kilojoules, so we have to convert that. Temperature in Kelvin. All right, and then our Q, remember our Q value here is our reaction quotient. Reaction quotient. And we dealt with this guy when we're talking about equilibrium, and we could calculate Q the same way we do with K, but we use Q at current conditions, whatever they may be, and then we compare Q to K in order to figure out whether or not we have our reaction at equilibrium or not. All right. Now the interesting thing here, they put this in parentheses, is that when we're at standard conditions, all the concentrations are 1, so our Q is always equal to 1. It doesn't matter if they're squares or cubes or anything. Everything is 1 because under standard conditions, concentrations are automatically 1 molar. So therefore, Q is 1, and the natural log of 1 is just 0. So this whole thing becomes 0 and it goes away. And so that's why this formula kind of explains that part of it. Okay. So remember, at equilibrium, our Q equals K and delta G equals 0. So if we take those two values and kind of plug them in, then we can also get this formula here, where 0 is equal to delta G naught, or star, plus RT natural log of K, rearranging. So we get two important formulas that relate our delta G and K. So if we have K and we want to find our delta G, we can use this formula, negative RT natural log K. Or if we have delta G and we want to know what our equilibrium constant is, we can use this formula here. So these two right here, these boxed in formulas, these are the gold standards. These are the big ones from this section here. All right. So let's see. So this problem here, it says calculate. Okay. Calculate delta G at 298 Kelvin for a mixture of 1 atmosphere 1 atmosphere nitrogen, 3 atmospheres hydrogen, half an atmosphere of ammonia being used in the Haber process. All right, so it's no longer at standard conditions because these are not 1 molar. So we got to use this new formula we learned, delta G equals delta G at standard plus RT natural log of Q. So first we got to find Q. So Q would be equal to the partial pressure of the NH3 squared divided by the partial pressure of the N2 times the partial pressure of the H2 cubed. So this would turn into 0.5 squared over 1 times 3 cubed. Where's my calculator? So 0.5 squared divided by 3 to the third. And I got 9.26 times 10 to the minus third. All right, so that's our Q value. Delta G naught, or delta G standard, I went ahead and calculated out earlier, so we didn't waste any time in the video. So delta G is equal, and for that I got negative 33.3, and this is in kilojoules per mole. All right, plus our R value, and remember our R value is 8.314, but it's got joules, so we got to divide that by 1,000. Times our temperature they give us is 298, times the natural log of our Q value, which we just got as 9.26 times 10 to the minus third. All right, so if we plug all that guy in, so negative 3.3 plus 8.314 divided by 1,000 times 298 times the natural log of that previous answer, and I got negative 44.9. But these guys all have 2 sig figs, so really it would be negative 45, and our units for this would be in kilojoules per mole. And there's that. Not too bad. All right, this guy says, which of the following statements is true? It says the larger the Q, the larger the delta G. Now, so the larger the Q, the larger the delta G standard. So I'm going to say, so if the standard wasn't there, then I think that would be true, but I think they're trying to trick us. Let's see what the other ones are and see if this was a typo or not. So B, it says if Q equals 0, the system is at equilibrium. That's not true. If G is at 0, then it's at equilibrium. If Q is at 0, that doesn't really tell us anything. Remember, you're at equilibrium if Q equals K, so that one's out. All right, C, if a reaction is spontaneous under standard conditions, it is spontaneous under all conditions. Well, that's not true. We learned that in the previous part when we talked about spontaneity, that we could, that in some cases can be spontaneous, but then if you change temperatures, then you become non-spontaneous, or vice versa, right? So C is just not true, right? And then part D says the free energy change for a reaction is independent of temperature. Well, that's just not true, right? We had delta G is equal to delta H minus T delta S. I mean, temperature's right there, so that one's gone. Okay, and then this one says if Q is greater than 1, then delta G is greater than delta G standard. Well, so what's the relationship of that? So delta G is equal to delta G standard plus RT natural log of Q. Well, if Q is greater than 1, that means this whole thing will be a positive value, because remember, if it's less than 1, you get a negative value and it would be less than, but because they said Q is greater than 1, so I think E is the right answer, because this would be adding to it, so therefore this would always be bigger than that, because you're going to add some number. It doesn't matter how infinitesimally small it is, it's still going to be bigger. So I think I was right to be sus of this guy right here. So we're going to say A is wrong and E is the right answer. All right, so here we go. Standard free energy change for the Haber process at 25 blah 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 is negative 33.3. Okay, this should be a 2 right there. All right. Anyway, when I put these in the big picture mode, the formatting gets all weird. Anyway, use this value to calculate the equilibrium constant. So remember, back here we had 2 different formulas. We had these 2 formulas right here. We'll use this one because we're trying to find the equilibrium constant. So K is equal to E to the negative delta G over RT. All right, so K is equal to E to the negative delta G over RT. All right, so we've got 2 choices here. They gave it to us in kilojoules and in joules. How nice of them is that to us? It doesn't really matter which one we choose as long as our R unit matches our G unit. So it would be E to the negative. Well, delta G would be, we'll just use that one, negative 33,300. And over R, which would be 8.314, times our temperature, which is 25 degrees Celsius, so that's 298 Kelvin. So here we go. So E to the negative 33,300 divided by 8.314 times 298. And I get a very big number. I got 6.87. How many sig figs do we want here? 3 sig figs, 2 sig figs from the temperature. No, 3 sig figs. So 1, 2, 3, 4, 5. So 6.87 times 10 to the fifth. And this would be our equilibrium constant, so it doesn't have the units. So 6.87 times 10 to the fifth. And so let's just think for a second, does that make sense? Well, so that would mean that this would be product favored. We'd have much more products than reactants. And delta G shows that it is spontaneous in the forward direction, which means it's very product favored. So yeah, I think that number does make sense. I don't think we screwed it up. All right, let's see. I guess we could say, they got the same. They only have 1 sig. Now, why do you think they only did 1 sig fig? Laziness? I don't know. All right, last bit here is about coupling reactions. Coupling reactions is a really interesting thing that happens a lot in nature, but doesn't necessarily, but also has a lot of really great industrial applications. But essentially, the idea is in a coupling process is that you have two reactions that are going on at the same time in order to give you favorable energy conditions. So this is the equilibrium where ATP and ADP are in equilibrium, and then you've also got this additional phosphate group right there. Okay, this additional phosphate group. And so that guy there gets added to form the ATP. And so this is what's going on inside of cellular respiration, right? So you've got your glucose coming in, CO2, turns into CO2 at H2O, gives you your ATP. And so this coupled reaction uses the energy released by the oxidation of glucose. Okay, and then that energy released by that gets turned into help your cells develop. Okay, so this reaction that's here producing energy gets used here to help you make those guys, help you grow or build bones or have energy to move your muscles and stuff like that. And that's just their example of a coupling reaction. But essentially what you need to know is that a coupling reaction just occurs whenever you have any sort of reaction that produces energy that allows another reaction that wouldn't be favorable to occur. All right, and that's it for the whole unit. You made it through the whole thing. Only one unit left to go. You can do it. Don't give up. It's been a long road. I know it's hard, but just keep on keeping on. Put one foot in front of the other, and you'll be just fine. Just do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.